optical sciences. And let me so I'm going to assume a few of you out there might not have been to the University of Arizona before. Big school, 43,000 plus students, 18 different colleges. And we're proud of our research profile. So we have a very big research agenda here. Actually, this number is outdated. We've got pushing $700 million now a year in research revenue. And in this area that NSF calls physical science, in part because it includes space sciences, we end up being ranked very highly in the nation as a leader. And that's because we do big science programs. The one that's the big science program right now in the space area is the OSIRIS-REx asteroid landing mission, where U of A, actually we're supposed to say U Arizona now. U Arizona is the prime on that, and they've selected their landing site. It's orbiting the asteroid, and they're going to land and bring samples back here to the university to try to understand the composition of that asteroid and learn something about the early formation of the galaxy. So here we are in the Hawaiian College of Optical Sciences, 3 buildings. You're in the newest of the 3. And this is kind of a quick profile of our college. We've got about 65 faculty that are directly in the college, about 35, actually 39 now, are tenure track. And we have about 25 research faculty as well. And then a large collaboration across campus with many other departments. So we have tentacles extending across the university. And typically about 300, actually I'm doing the count, 314 graduate students as of fall semester. And it's about 170 PhDs, 130 masters, and 10 or 15 certificate students. And a significant undergraduate program, about 38 students on the average per class. And they don't enter until they're sophomores because they come in as freshmen. And we don't try to recruit out of high school today because nobody knows what optics is. And we're divided on within the college on a research agenda perspective in 4 different areas, but they're not departments. Maybe someday in the future we'll have departments, but today we're still compact enough where we have one unit, and these are self-organized research areas. So it's optical physics and optical engineering are the original core strengths of the college, going back to the 1960s when it was formed, and very fundamental physics, and then optical engineering, which is really designing imaging systems and optical hardware, fabrication, high performance imaging systems of all kinds, and illumination systems. And then in the meantime, we've blossomed into 2 other areas, image science and photonics. And I've described what that was to the students. And over the last couple of days, they've had a lot of exposure. I'm going to get into that in a minute. But one of the interesting new pieces of news we've got for the college is we're growing very rapidly. And it's a result of investment from our community, a large injection in our endowment here at the college. We're going to be reaching about $42 million of endowment. And with that, and co-investment by the university in the form of startup packages and just the way the finances work in the university, they're co-investing to allow us to grow by 14 new endowed chairs, thanks to donors, and some of those donors are here in the audience, so it's very exciting for us, and we're just launching that campaign right now. And we will also, to house all the new growth, is a new building. So in the parking lot that many of you maybe crossed coming in this morning, behind us, and we're going to have a new 100,000 gross square foot building, and optical sciences will occupy about 30,000 net assignable square feet. Actually, that amounts to about half of the building, and more than half of the building. And it will also have meeting room and classroom space as well. So that ground will break on that later this year. Very exciting. I'm sure it'll be a little bit disruptive, but it will be completed by late 2022. And the areas that we're anticipating growth into are shown here. This is just a snapshot of some of the strategic thinking we've been doing about the college, but investing in new advances in the area of hardware, optical systems, and autonomous systems, and artificial intelligence influence systems, increased investment in biomedical optics. We're already very strong in space science technologies here at the campus, but we want to encourage stronger linkage from optical sciences, and we're getting deeply involved in quantum information science and providing advanced materials, and also this area of optomechanics. So we will continue also to invest in our core strengths. So we're not walking away from any of the areas we're very good at, and we will be investing there as well. So the workshop, now to welcome you, it's a multi-day event. This shows the profile of the participants. It's 55 students from a very, very broad spectrum across the nation, 32 institutions or enterprises participating, and it started out focusing on primarily undergraduate institutions, but now it's expanded, and we're very excited to be able to host this here in Tucson. It's way back when this might have been a parochial event thinking about recruiting students here, but now it's really recruiting students nationally into the field of optics and photonics. So we're excited that we've got participation from all these different institutions, and many of the faculty from these universities are here speaking over the next couple of days, and some have already been speaking over the prior 3 days. So it's really an opportunity to highlight optics and photonics for the nation, try to get more students interested in it and understand how broad it is. So here's where we were. The first 2 days we had the winter school, and the objective there was really exposure. Just many students don't have a chance to see how broad the opportunities are in the field. And so this is a little bit more about a deep dive into what those science and technology areas are, and it's really focused on research. And this is you can't read this probably, but it was a 2-day intensive exposure to somewhat organized around the areas I described earlier about image science and photonics and optical physics and optical engineering. And our faculty, by the way, this is a faculty self-organized event, so I'm very, very excited that our faculty are willing to put so much energy into this. And again, I thank all the speakers who are coming today and tomorrow to contribute as well from across the nation. Yesterday we had what was Immersion Day, and I think I scared everybody when I showed that picture. But it was actually a very, very busy day. So in the morning we had 15 faculty-sponsored opportunities for students to go in and actually tinker in the labs with real stuff, ongoing experiments in many cases, just to see what the lab experience is really like. And then in the afternoon, everybody got a break and got to, I think most people, 45 people went up to hike and, or walk or hike in Sabino Canyon. And then last night we had a wonderful dinner and a great student poster session. So I was excited to see all the posters from the students. Really, really good work going on, and it's fun to see. So now the next 2 days are where we are now, and the shift, this is now called the Winter Workshop, and the shift in focus is really about highlighting not so much discipline-based work, but to just illustrate some outstanding work across the nation from faculty and a smattering of events and talks that are really based around careers. Like why did people get interested in optics? Why did they go into the field? We'll have a panel session to discuss that as well. So the purpose here is to talk about career opportunities, but also to share teaching experiences and from across the nation, some of the ideas that people have about how to improve the curriculum or add new laboratories and things like that. Again, focused on, in a lot of cases, students coming from primarily undergraduate institutions don't have as intensive a portfolio of research going on at the graduate level, so it's harder to get a sense of what's going on. So the idea here is to continue that exposure. We have some really outstanding speakers coming. So we have colloquium talks that are in the agenda, And those are longer talks. Jim Wyant's talk will be this evening. And then we have workshop speakers, as you see, from across the country. So here's a snapshot of the morning. This is where we are today. And 3 minutes late, so I'll get off the podium in a second. And then in the afternoon we have more talks, including more colloquial talks. And then in the evening tonight we have a banquet and a great talk by Jim Wyant. And then tomorrow, again in the morning, starting off with some exciting colloquium talks, in this case on the NIF facility, and through lunch, and then in the afternoon followed by dinner. So I want to end and just thank our sponsors. This is an expensive event. We pay a lot of support to get students here, but we're also excited now that a lot of the participating institutions are contributing. So, as I said, it started out as a somewhat parochial event, and it's in its 5th year now, and we're really excited to see this transition to having this be a sustainable national event to get students into the field. It's a wonderful thing to do, and I think as a result of that, we've been happy to get support from foundations and the professional societies as well. So, without further ado, I'm going to allow invite Daewoo Kim up to the stage to introduce our first colloquium speaker. So, Daewoo.
Thank you, Tom. Good morning, everyone. It's a beautiful morning. The sky was blue, the air was fresh. I think this is just a perfect setting to be together as a science community like this and talk about education, our mission, science, and all the discoveries as a human being all together. So once again, welcome to this winter workshop. It is my great pleasure to introduce our first keynote speaker, Professor Dan Marrone. Some of you know why I switched my major from astrophysics to optics 15 years ago. Because I loved the experimental aspect of optics. If I met Dan maybe when I was a student, maybe I changed my career path. Because Dan is an experimental astrophysicist in the Department of Astronomy at the University of Arizona. His research addresses galaxies and cosmology, even fundamental physics. He is interested in galaxy clusters and their cosmological applications, galaxy formation in the early universe, and of course, the physics of the supermassive black holes. To investigate those topics, he often developed new instruments, primarily at centimeter to sub-millimeter wavelengths. His scientific interest and vision is exceptional. But in addition to those scientific vision, he has great passion and track records. Since he received his PhD at Harvard Astronomy in 2006, he was the Jansky Fellow in 2006, Hubble Fellow in 2009, received Koch Prize in 2013, and the Breakthrough Prize with Event Horizon Telescope EHT team this year. Finally, in my opinion, one of the most objective number representing a scientist, he has published more than 190 refereed journal papers. So now you can guess his most recent project and amazing scientific achievement. He is the PI for the EHT Event Horizon Telescope project at the South Pole Telescope. He also coordinates a modeling and analysis working group and is the vice chair of the EHT Science Council, which is a group of 10 senior scientists who oversee the overall telescope project. So now, please welcome Dan for his talk for the taking a photo of the very first black hole in human history. Thank you.
Hope it works. Hope my computer turns back on. There we go. All right, let's see if the colors are correct this time. Let's see. There we go. Hey, look. It's a not. Yeah. All right. Thanks a lot, Daewoo. Such a lovely introduction. So, thank you everyone for coming and listening to me talk. I am going to talk about this picture. Who's seen this picture before? Yeah. Be nice to surprise an audience once. All right. So, of course, I am a professor here. I'm a professor of astronomy here. But when I give talks about this picture, it's really important to point out that this was a massive effort, just an enormous number of people. There are 337 people on the papers, and there are close to 300 members in the collaboration now, and so it really is for the Event Horizon Telescope collaboration. This was maybe 150 of us last fall. There were fewer of us at the last collaboration meeting because it was harder to get to, so I show this one. The EHT has board institutions, and it has all these other institutions. It has all these sponsors, and it's important that we show all these things. These are Major League Baseball logos from 19. Anyway, with all of that out of the way, let's talk about supermassive black holes. So this talk, is close to the one I give in any astronomy colloquium. I've tried to tune it a little bit to make sure that people who might not sit through a lot of astronomy talks get a little more background, but if that's too much of it, I apologize in advance. So let me start on a little bit of that. These aren't pictures of black holes, right? These are pictures of galaxies. But for 20 years, we've been pretty confident as astronomers that there is a supermassive black hole at the center of basically every galaxy. And interestingly, actually, when we look at the mass of the supermassive black hole, it is very strangely tied to the yellow parts of the galaxy in the middle. The distribution of stars at the centers of each of these galaxies on scales much larger than the black hole can directly influence are the speed those stars move, the velocity dispersion, is connected in ways we don't fully understand to the black holes. Clearly, the black holes are intimately connected to the way you grow a galaxy over the history of the universe. So we don't understand that, but more than that, we don't actually understand how you grow a black hole. The basic idea is simple, right? Stuff falls in, it gets more massive. But it's actually not that easy to get a lot of stuff onto a black hole, and in periods when black holes aren't growing, which is the case for basically all of the galaxies you see here, they're accreting very slowly onto their black holes. Understanding how that mass is getting down and what stopped stuff from falling in or greatly reduced the rate is a really interesting astrophysical question. Another feature of black holes, and you can see it in that galaxy over there, is that they very often have these very powerful jets. That weird-looking thing that's sticking out of the galaxy, that is a jet launched from the black hole. It's material moving at nearly the speed of light away from the black hole. We also don't know exactly how to do that. In astronomy, at least, we think we understand a physical process when we can simulate it in a computer and reproduce it. In the case of astrophysical jets, we can reproduce them, but we can reproduce them in many different ways, and so that shows us that we don't really understand what's going on. And finally, these black holes can provide us a view of fundamental physics. They're laboratories of general relativity, which is Einstein's theory of gravity. We study general relativity, and in fact, we're entering a real golden period for astrophysical studies of general relativity with things like LIGO, observing black holes merging directly. But those black holes have masses of 20 or 30 solar masses. The black holes at the centers of galaxies have masses of 1 million to 10 billion solar masses. And so, if there are any problems in this fundamental theory of relativity, oh, that'd be nice. Thanks. I can accidentally shoot you guys. if there are any problems with this fundamental theory of gravity, then this is a way to test them. We'd like to explore our fundamental physics theories in all the regimes that we can. Now, if there's a black hole in every galaxy, then there ought to be one in ours. And in fact, these two telescopes are helpfully laser pointering out this black hole in our galaxy. It's called Sagittarius A star. It's sitting right there. This is a picture of the central arc second of the galaxy. Central arc second, central 15 arc seconds. You know, if you zoom in, you don't see the black hole really, but we know there's one there because we've been watching stars go around a blank spot in the sky for more than 20 years now. And so we've actually been able to track stars orbiting this spot on the sky and seen complete orbits. And if you can get an orbit and a velocity at any point in the orbit, you can solve for the mass that's being orbited. And there's about 4 million solar masses at the location of this black hole. There are other black holes, and in fact that image that I showed you before was actually an image of the galaxy M87. It's the central galaxy in the Virgo cluster of galaxies, which is our nearest cluster of galaxies, and we're sort of slowly falling in that direction actually. And this jet has been known for more than 100 years, even before we had any idea what that could possibly be. It was noticed in people looking at M87. It's also visible in the radio and in the X-ray. This black hole just happens to be about 1,000 times further away than the one in the center of our galaxy, and it's 1,000 times more massive. And general relativity says that the size of the black hole is just proportional to the mass, and so this is approximately the same angular size as Sag A star. And you know, I highlight these two black holes because if you look out at the universe and you say, all right, if I have a telescope that is the diameter of the Earth, and we're observing at, say, a wavelength of 1 millimeter, how many black holes could I resolve? And unfortunately, there are only 2. But fortunately, there are more than 0. And the whole EHT project would have been quite significantly more pointless had it not been for those 2 black holes. Ooh, that's good. Okay, and so, you know, the EHT was built to do those things I said. We'll test general relativity by looking close to the event horizon. We will see material falling onto a black hole, even circling the drain, and watch how accretion happens. And because we can make polarized images, we can see the magnetic structure where the jet's being launched. If we look at M87, we know there's a jet. We can see it coming out. And at longer wavelengths, we've seen almost all the way down, but we don't have the sufficient angular resolution to see the black hole, and another property I'll tell you about in a second. And so this will really get us down to what is creating that jet. We can look at other sources too, but it's these 2 targets that are bright enough and big enough on the sky that allow us to see black holes directly. You know, it didn't have to work out that there were any. It also didn't have to work out that we could see to the event horizon. It turns out in most black holes you can't. If we were observing at 10 times longer wavelength, we'd have a problem. This is a simulation of Sagittarius A star at a wavelength of 1 centimeter instead of 1 millimeter. And you don't see the black hole at all. In fact, you know, if you run this movie forward, we move in wavelength from 1 centimeter to 1 millimeter. You see, you have to get pretty close to 1 millimeter before you actually are seeing the event horizon. Even at 3 millimeters, the size of Sagittarius A star is 15 Schwarzschild radii, or you know, 7.5 times the diameter you might expect for a black hole. And so we are very lucky here. The problem is that the synchrotron emission is just optically thick. At longer wavelengths. And if we wanted to go to shorter wavelength, we have some problems. We'll push the HT to 345 gigahertz, but which is, you know, a factor of 1.5 higher frequency than we've done so far. But beyond that, the water vapor in the Earth's atmosphere prevents us from having a clear view. It absorbs all the light from space and emits thermal radiation to our telescopes. So we can't really do this at any higher frequency from most places on the ground. All right, so how do you build a telescope the size of the entire Earth? We use a technique called very long baseline interferometry. Basically, radial interferometry, normally we receive the electric field at each telescope, we put it on a wire, we send it to a computer that doesn't sum those voltages, which would be more characteristic of optical interferometry, where you're just superimposing the light, but instead multiplies them. That effectively does the same thing, but it is systematically favorable. It controls your sensitivity to variations in your system. And there are other reasons to do it. But in this case, obviously, when the telescopes are separated by 10,000 kilometers, we can't really put those voltages on a wire and multiply them. And so instead, we put atomic clocks at each site, and we very precisely time tag the arrival of all the photons, and we record them on disks. And we ship entire crates of disks to central locations where our correlators multiply those voltages for us and interfere the light as though we had focused it onto a spot. Kind of, because we're multiplying instead of adding. But the math works out basically the same. So that's the principle. The measurement we make, and this is always a tricky part, but maybe less tricky for you guys than for most, is we're not actually taking pictures. We're measuring the Fourier transform of the sky at very specific spatial frequencies. The angular, the frequency with which a plane wave oscillates across the sky. So, high spatial frequency is very small angular scale fluctuations, and low spatial frequency is very large angular scale fluctuations across the sky. So if you have two telescopes that are separated by some distance, L, then the spatial frequency you'll measure in the sky is L over lambda. The spatial frequencies we're talking about in EHT are of order 10 billion wavelengths. So the angular size is 1 over 10 billion wavelengths. 2 times 10 to the 5 is 1 arc second. So this is a small number. And so one baseline will give us one spatial frequency and another measurement that's just the complex conjugate of that thing. It's completely the same. But as we let the Earth rotate, we can fill those in. And so here's Spain to Chile, and then we start adding more sites as the source rises for them, and we fill out this Fourier plane, and we get a black hole image. It's not quite so simple, but it's close to it, that simple. Reconstructing the image is a bit tricky because we can't preserve the phase entirely because of the atmosphere. This experiment is something we've been doing for a long time. I started work on it in 2005. The first experiment was 2006. That failed. The first experiment that succeeded was 2007. We did, through 2013, experiments that were just 3 telescopes. There's always been one in Arizona, and there's a site that disappeared in California, and then there's Mauna Kea in Hawaii. And with that, we convinced ourselves that the black holes in these 2 prime targets were about the right size for us to see them. This is the visibility as a function of telescope separation in, this is 3,000 million wavelengths, so 3 gigalambda out here. If the source were a point source, this would be constant. And if the source were really extended, then this would fall off more quickly. But because it falls off with about that rate, it suggested to us that these were about the size of the event horizon of the black hole. And we really should go see if we can make a more detailed picture. And so since those early days, we've been working on expanding the array. This is what the array looked like as of 2018, where we added telescopes all over the Earth. The South Pole I'll talk about, also Greenland. We're adding another one in Kitt Peak this year and another one in France this year. But we've really built out the array so that we can make better measurements of black holes, and that image you saw was evidence of that. I'll talk about the South Pole a bit because it's an interesting place and because I've spent 10% of the last 5 years there. outfitting the South Pole telescope for this experiment was a lot of work. It's been an interesting challenge. This is the South Pole telescope. It's a 10-meter radio telescope at the South Pole. It's designed to work at, say, its main science is 2 and 3 millimeters, but it's designed to work up to 350 microns. And it doesn't have the right instrument to do this kind of experiment. We need to coherently measure the electric field, and its detectors don't do that. And so with this very sophisticated system diagram, I can show you what we did. We went down there and we put an atomic clock over here, and we put some cable there and ran it up through the telescope, and put a bunch of data recorders here and put a receiver there. And if you look closer, we're basically cramming our receiver in behind this massive structure because the telescope wasn't really built to do this. But it was interesting enough that it seemed worthwhile, and has proven to be worthwhile. Are my colors weird again? Oh, that's great. I wonder what's going on today. Never had this problem before. Maybe it'll come back. Everyone looks like a science fiction movie. All right. What can you do? So, how did we do this? Just since it's career day, a little bit of, extra behind-the-scenes history here. This is Ghost Me. I've got to do something about that. We're putting together the very earliest stages of the receiver in the lab. Let's see what happens if I try again. Hey, look. All right. I mean, I haven't been touching it. That's the funny thing. It's flickering on its own. All right. So, there's us just getting started. She's a grad student at RIT now, and I saw that on the list of institutions here. This is the heart of the receiver. There are precisely 2 pixels in this receiver, 1 at each frequency. That is the 230 gigahertz receiver, and that's the 345 receiver. The light here is actually coupled into a horn with even a shaped profile into it, so that we can precisely launch a Gaussian mode at our wavelength. The aperture is only a few wavelengths across, so it's a real electrical engineering and physics task to design these horns. And then once you're out of the horn, then it's Gaussian beam optics, because all of these, typically in submillimeter radio astronomy and all of radio astronomy, we have apertures in our systems that are comparable to our wavelength. So diffraction is important. Here's us at the South Pole just a year ago, almost exactly. Junhan, my former grad student, just graduated last year, is on his way down on Monday, and I don't have to go this year, hooray. That's us about to put it back on the telescope. That's how we do it. Once we get it up on the roof, we carry it in and drop it in a hole. There's, satisfied us that we haven't broken it for another year. It's safely into the hole. Here's some of the other equipment. This is, how much recording equipment we use. Each of these is holding 8, say, 10 terabyte drives, so 80 terabytes per. There are 16 of those times 8 is 128 of those spinning at once. So it's a petabyte of spinning disks to record this. Atomic clock. Here's the optics that we use. Actually, this getting this thing to work is a lot of different metrology challenges. This is just examples of it, but here's us aligning the telescope system for the main receiver, but also for the EHT receiver with photogrammetry. Here's ferro arm that I borrowed from OpSci in our lab, making measurements of the mirror mounts. This is actually, you can't really see it, but there's a little waveguide launching 230 gigahertz radiation at the horn here, and we're sort of scanning the electric field above the receiver to make sure that the beam is nice and Gaussian and is launched from the place we think it should be in the cold receiver. And here, even cruder is us using the inside micrometer at minus 40 C or something like that to make sure the mirrors are the right distance apart and properly aligned. You know, from those initial experiments, the technology has advanced a lot, fortunately, and made this work much better. It was quite hard, those first few experiments, and it's relatively easy now. Our detectors are much better just from the massive international investment in them for something called the ALMA project, an Atacama Large Millimeter Submillimeter Array in Chile. These atomic clocks are now commercial. We can buy them from 2 different vendors. And you know, for $250,000, you get as precise an oscillator as you could ever want. Hard drives, of course, have gotten much bigger, and electronics have gotten faster. So, you know, we were recording 4 gigabits per second, and now we're recording 64 gigabits per second, and that difference means that we're, you know, 4 times more sensitive just on that basis alone. Skip that for sake of time. Okay, so we've built out the array. The technology's improved. We think, as of 2017, that in principle we should be able to take a black hole picture. And so our first opportunity to do this was my 38th birthday, I guess. That's my birthday. Which for the 4th time, I think, I spent on a mountain doing AHT observing. Anyway, so we all went to our respective telescopes. These are our 2 winter rovers at the South Pole because you can't get to the South Pole in April. So they're marooned down there. I was at the SMT in Arizona. Well, we all went to these sites. We got our systems ready. And we all collectively pointed our telescopes at it precisely the same times at this thing, which is, again, M87. And it's black hole M87 star. And so with that, we have our array scattered over the Earth, and in April 2017, we took 5 petabytes of data, which is a lot of data. It's, you know, if you lined it all up on a table, those modules would stretch across this room roughly. I think I said in the NSF press conference that it is the lifetime selfie collection of 25,000 people. It's a lot of data. And so in November, we had those data finally, and we do a thing called correlation, where we look for the exact same wavefront arriving at each telescope. You know, we know the geometric difference in arrival time because we know the surface of the Earth and where the telescopes are, but the atmospheric delay varies slightly, and those atomic clocks that we have at each site aren't actually precise in frequency, and so our time basis is slightly wrong. And so we have to shift the data relative to each other to find the same light arriving. And we also have to stretch it in order to get the wavefronts to add coherently. But once we do that, and once the screen is done flickering, this reduces our data volume by a factor of 1,000. We can do a factor of 10,000 more by basically taking out the ripples in the atmospheric phase over time, and then when we make an image, it reduces the data volume by another factor of 1,000, so that we're down to an image like this with a few hundred kilobytes of information, starting at 5 petabytes. This was a lot of work, and I always do like to recognize the sort of central core team who did this. There's a lot of software developed purely for this. They're grad students and postdocs, and now CK is on the staff here. He's an astronomer here, it was a big project and took them a great deal of effort. You've seen this image for scale. Let's go with it. For scale, this is who knows XKCD. Anyone? Yes. Okay. So a couple XKCD comics about this, but this is the solar system to scale and the farthest any humans have ever launched anything. It's a big black hole, but it's 55 million light years away, and so it doesn't look very big on the sky. This is 50 or 42 microarc seconds across, it appeared ghostly on newspapers all over the world. That was quite a thing, I must say. I went to Washington, D.C. to do this press conference, and, everything. I flew out the next morning, and as I walked through National Airport, the newspapers all had our picture on it. It was quite a thing. But of course, there were contrary opinions, let that simmer while I try yet again to make my computer behave. Okay, and so, all right, whether the image is pretty or not, I think the interesting question as an astrophysicist is, what are we actually learning from this? It is an image. I will give myself that. I'm happy that we have it. But let's talk about what this image actually tells us. And so, what I want to talk about is the measurement we make, which is not an image. And it's really important that, it's true that we can create an image that looks like a ring, but how do we know that's the right image when we're starting with a very sparsely sampled Fourier transform of the sky? How many of you have worked with or dealt with Fourier transforms in any sense? All right. How many of you have never heard the two-word phrase Fourier transform before? That's good. So this is this plane in which we're denominating the locations of the separations of the telescopes in wavelengths, and so billions of wavelengths, in fact. And this is all the telescope pairs we have in our array, at least for 2017. And so this is the full set of measurements we've made, and this is the amplitude of the correlated signal between the pairs of antennas as a function of radius in this plane. So all those colors correspond to colors here, and we're seeing that at short baseline lengths, the amplitude's higher, and then it's lower out here, but there's some interesting structure here. So can we understand that interesting structure? And so let's try. Imagine that what we were looking at is just simply a disk, and we're just going to change the size of the disk. What would that do in this amplitude versus baseline length? So in red is those same data points that you see here, and in yellow is the Fourier transform of that disk. And I'm going to vary the size of the disk, and you see that if you make it bigger, you can match this fall off quite nicely. But you also see that you don't match anything after it. So this is not a free enough model to match the way our data look. But if you want to make it slightly more complicated, you might take out the center. And so if you do that, and you change the size further to sort of optimize this, change the size and the width, you see you can do much better. You still match that fall off. You match this place where the signal goes low. You mostly get it right here, and you mostly get it right here. If you want to get it even more right, you notice that blurring in the sky, which is convolution with, say, a Gaussian, corresponds to multiplication with a Gaussian in the Fourier plane. So it would be a taper, a sort of Gaussian fall off in radial distance here. And so if you do that, you see you can match this part quite a bit better. And you're doing pretty well. So our data pretty strongly say that there should be a ring-like thing in this. And in fact, before we were ever successful in making an image, some of us were sitting, all right, this is going to work out pretty well because we could see this in the data. But you say, Dan, if you're paying attention here, you are completely missing those points, right? You're not actually matching the data that well. Good point. But there's also actually a pretty simple explanation for that, because if you look at where those data points are, the red ones here are the ones that we're missing. Those happen to be the ones that are in these north-south baselines. And the blue ones, where the signal goes down more completely, are east-west. And so what this tells us is that the image is asymmetric north-south and not asymmetric east-west. Because if it's asymmetric, then the signals don't cancel quite as perfectly, and it doesn't null out the same way. And in fact, if you remember the image, that's exactly what we ended up seeing. The signature of this ring, this asymmetric ring, is very much imprinted in these data. It had to come out this way. Now, all of that said, this was an important discovery, and we wanted to be very careful about it. And so we did a lot of tests. We made our images with 3 different techniques that are independently derived. This is sort of the classic technique of radio interferometry. It's called the clean algorithm. These are newer approaches. The images differ from each other because they differ in how they weight the different baselines. But they agree with each other from day to day. Each method agrees with itself quite consistently, and the basic properties, if you blur them similarly, are identical. We also wanted to know that if we looked at something that wasn't a black hole, we wouldn't see a black hole anyway. So we created a lot of fake data, and we ran it through our algorithms. And so we feed it rings, even really complicated rings, we should get rings. And if we feed it things that aren't rings, we shouldn't get them. And, that's what we found, right? This is manifesting some of the known failure modes of radio interferometric imaging, which doesn't see the total intensity on the sky. It only sees these higher spatial frequencies, so it doesn't reproduce extended objects very well. But the rings come through, and we don't create any rings where there aren't rings. And we did a lot more tests than this. So what does all of this mean? Here's the main features of this thing. You see the north-south asymmetry. I talked about that. You see what we've referred to as the black hole shadow. This is the expected property from general relativity if we're looking at a black hole. Basically, even though there's emission coming from all around this black hole, in front of it, behind it, above it, below it, the stuff in front has a hard time getting to us because gravity is pulling those photons back. They're coming out. Very few of them escape. Most of them get bent back, get lensed around the black hole. They may orbit it, they may fall in, but they don't come straight to us from here, so we don't see much light from there. And so that is the sense in which this is a neat visual confirmation that general relativity is describing the black hole. Now, in that sense, it's only a qualitative one. We have more, yes. We have more physicsy ones, but I'll get to that a little bit in a second. All right. First of all, is this what we expected to see? Well, this is a simulation of a black hole. This is the image. They don't really resemble each other, but if you subject this to the exact same measurement technique, this Fourier transform and reconstruction, you find that even though this isn't tuned to match that precisely, it matches it pretty well. Of course, we're doing this, in 2018, and we already knew the answer. So is this really what we expected to see? Well, you can actually go back through the literature and see that there were papers written that do a pretty good job of predicting this. This one's from 2012. There are others without ever having seen the image. The only thing this paper gets wrong, this is taken right out of the paper, except it's rotated 180 degrees because we didn't know the angular momentum vector of the black hole before that paper was written. I'm not on it. But if you do the same thing for this, it will also match the image quite well. That north-south asymmetry tells us the angular momentum vector. And so I'll talk through this with my hands while it's rebooting, but the black hole's spinning, and that jet is actually coming towards us almost perfectly. It's only 15 degrees from our line of sight. You can tell because as you see blobs of plasma move out, they appear to move at faster than the speed of light across the sky because light emitted back here has to catch up with light emitted out here, and the material's moving at almost the speed of light, so that blob seems to move faster than it should be able to. Anyway, we've known its orientation for a while. We just didn't know the spin vector. And so this is telling us that the material is rotating towards us on the bottom and away from us on the top, and so that means the spin vector is into the sky. Most interesting astrophysically, perhaps, is that we may have weighed M87 star. So M87 star is the supermassive black hole. There were 2 measurements of its mass before this experiment. One from the motions of stars said that it was about 6 billion solar masses, and one from the mass of from the motions of gas said it was half that. Typical of astrophysics, we have no idea what the right answer is, but we are very confident in our two answers. Oh, I didn't take that. Ignore that. You can't go see that talk. That I copied this from my slides from Monday, and I should have taken that off. But anyway, our measurement falls pretty convincingly on this higher mass. And the way that we get that is from the size of the ring. General relativity says that the size we see for a black hole ring should be just the mass over the distance times fundamental constants and times this prefactor in appropriate units. And so that's because all this light you see, these are just different simulations of the black hole, but they have this common feature that there's this lensed light that really is a prominent feature. And so if that's the light we're seeing, this stuff that's just barely escaped the black hole, then we're measuring the mass. It's actually possible that we're not seeing that this stuff is what's dominating our emission, in which case the image would look larger than we expect, and the mass would be the lower one. So we may not have measured the mass. The best case we have for this is that when we look at the data very closely, when we look at the Fourier data, not the imaging data, we see that they want our image ring to be extremely sharp as the data could hope to measure. This is half our resolution, so this is, suggesting that the ring should be quite fine. And so this, from the data we have so far, this is the best case we have, that we have the mass. But as we go into the future and we get better data, we will much more convincingly measure the mass. If I was talking about Sagittarius A star in our galaxy, we would be talking about testing general relativity, really. Because in the case of Sagittarius A star, we don't have this two-mass problem. Because we have these stellar orbits, we know the mass of this thing extremely precisely. So this is the distance, this is the mass. That ratio is what's going to determine the angular size. You see this? This is to far better than 1%. This is, that's 0.02 million solar masses on a 4 million solar mass thing. And so we know this thing, and when we get an image of Sagittarius A star, then we should be testing general relativity more precisely. If the ring is the wrong size, I guess our first fallback will be that there's an astrophysical problem, but it might be telling us there's a general relativity problem. The reason I'm not talking to you about Sagittarius A star, who knows? Do you know why? Well, because we haven't released an image yet. But the reason we haven't released an image yet is because Sagittarius A star varies quickly. That black hole, this is data from when I was a grad student. But anyway, Sagittarius A star over the course of a night will vary dramatically. And we've known that all along because things can orbit that black hole in as short as a few minutes. And so we have to deal with the fact that our target is changing shape all the time. But we're making progress, and I can tell you with significant confidence that sometime this year we will release an image of Sagittarius A star. We'll also tell you about the polarization structure around M87 star, which will tell us about that the launching of jets. And we have just submitted a paper on a non-horizon source, a supermassive black hole where we can't see down to the event horizon. We don't have the resolution, and it's optically thick. But interesting stuff still happens, and we have a lot of those. And so that's coming up. On Mirror Earth in this weird color scheme, we're going to take more data. The 2020 array, we're getting ready right now. In fact, I'm going to be up on mountains for the next month in Arizona getting these two ready. And as I said, Junhan's going to the South Pole to get this one ready. But we're adding Kitt Peak this year. Greenland has already been in. France is coming in this year. And that'll make a big difference because if you look, black is what we had in 2017. Blue are the baselines we're adding in the 2020 data. We will have a significantly better data set to make these images when we take data again. Slightly longer time scale. We're going to push this experiment to higher frequencies. It doesn't really matter what fake color scheme I put in for this, but let me put it to the one I chose instead of the image of that. this is all I can show at 345 gigahertz, but we've actually done experiments now that where we've done interferometry at 345 gigahertz. The highest frequency it's been done, very long baseline interferometry. But this isn't that. This is just a map of the moon we made last January at the South Pole. That's what the moon looks like at 345 gigahertz. You can see some common features, actually. You're seeing the thermal glow of the dust as the from the solar illumination. And we're also going to be okay. On longer time scales, we're trying to add more stations. The more information we get, the prettier the pictures we can make. And so, these are likely candidate sites all over the world, and even longer time scales, but perhaps not that long, because we can do this with almost CubeSat scale things. We can do space VLBI, which is a thing that's been done multiple times, just not at these frequencies, but would significantly enhance our ability to make black hole pictures and black hole movies. So, look out for more results, and yeah, thanks.
Thank you very much. It was very nice to be surprised twice by looking at this beautiful blue black hole. That was also, very special. But thank you so much once again. We have time for questions. So, anyone has questions from the floor? Yes?
You said in 2006 you tried it for the first time and it failed. What was the problem?
So the problem, almost certainly, this might not be right, but this was the best explanation we came up with. Back then, we could only record one polarization at a time, and it seems that because of the difficulty of confirming which polarization is which, we were recording a different polarization at one telescope and another, and so the only thing that correlates when you do that is the linear polarization from the source, which is only a few % of the signal, so we just didn't have enough sensitivity to see that. But the next year, we very thoroughly checked whether we were connected to the right receiver output, and it worked fine.
Yes.